class recording has started, so let's please make sure that we keep our side conversations down to a minimum so that we can hear the questions and the answers to questions. All right? So, Paige had a question first. Before we started recording, So, Paige, go ahead.
Okay, on the objective sheet.
Yep.
When it towards the bottom, it says determine the formula for a covalent bond given the name, and then it says determine the name of a covalent molecule given the formula.
Okay. So, as far as the objective sheet goes, for where was it here? There we go. All right. So as far as this goes, okay, Paige, this gets into the chart, right? That if I give you a name, you should be able to use that name to then figure out what the formula for that compound is going to be. Something like on your quiz, I think I gave you something like this: dinitrogen tetroxide. Okay? So I gave you dinitrogen tetroxide on your test. You should be able to take that and go, okay, what would the formula for this be? So first, the formula tells us what kind of elements are in this compound. So what kind of elements are going to be in this compound?
Nitrogen
and oxygen. Okay, that's the nitrogen part, that's the oxygen part. And then the prefixes tell us how many of those different things, right? So Paige, how many nitrogens are there? 2 because of the di prefix, right? And then how many oxygens? 4 because of the tetra prefix. Okay? Yes, Sean?
And then the one after that is like just switching it around.
Going backwards, right? So if I give you this formula, right, like this, that's then going, okay, I know that the name has to include the name of the 2 elements, right? Then the prefix is to tell me how many, so that's how we get to the, dihydrogen monoxide. Eric, good.
I have a question about the lab.
Hold on a second. Let's finish up this first. Are we good as far as this is concerned? All right. Do you have a question related to this?
Yes.
Okay, go ahead.
If it's in the first element and it's just 1, you don't have to put the mono.
Exactly. So if we have something like this, right, CO2, right, this isn't monocarbon dioxide. If the first element only has 1 of those, you just drop the mono, so this is just carbon dioxide. Good there? Questions on this one? Sam?
on the lab.
Objective sheet or on lab?
On the lab.
On lab. Hold on a second. Okay, recording back up. Sam, go ahead.
Number 1 on the back page.
Number 1 on the back page. Number 1 on the back page says, explain how the type of bond could determine the volatility. So, we explained volatility real quickly before we did the lab, but this turns out, how did we measure the volatility of something? What did we look for or what did we look for to test? Okay. Volatility means smelly, right? Right? That's not technically what it means. It means, like on the front page, if it turns into a gas, right? But then on Friday, we talked about, the beginning of our discussion Friday focused on states of matter. And what did we say about gases? What was true about the particles that make up a gas? They're real far apart. What else do they do? Say again? Yes, that's sort of a reason why they're flammable. So they're really far apart. This is more like a reason why they're flammable. So this question and the flammable question are actually kind of the same answer. Okay? So they're real far apart. What else?
And it fits its container.
Fits its container, right? What else should we say about the particles? They're real far apart. What else?
They move a lot.
They move a lot. They move real fast. Are they attracted to one another?
No.
Not very much at all. Okay? So, Sam, something that's volatile tends to turn into a gas easily, and that means that the particles aren't very attracted to one another. That was really sort of one of the properties of what kind of bond, which covalent to be specific. Because there were 2 types of covalent bonds that we talked about, right?
Polar covalent.
non-polar covalents, right? What did we say were some of the or what makes something non-polar covalent? Let's talk about that first. Eddie, go ahead.
If the difference between the two substances is less than 0.4.
Difference in what?
The difference in their electronegativity.
Difference in electronegativity, negativity, is low. And we said that was like between 0 and 0.4. What does that mean if they have very similar electronegativities?
They are similar elements.
They, not necessarily, but they have a similar attraction for what? For electrons. Okay? So, if we have a non-polar covalent, what does that mean within our molecule? They're the same what? The same attraction. So if I drew something that looked like this, the same attraction for electrons, if I drew something that looked like this, and here's one atom and here's another atom, would one side have a bigger electron density than the other side? No. So we don't get any of those quote-unquote positives or quote-unquote negatives, right? Now if that's the case, right, if another one of these things comes close, is there anything to hold them together? No. So how hard is it to separate the two of them? Really easy, because there's nothing holding them together. So say back to the question, things that are volatile turn into a gas really easily. How hard is it to separate those things? It's pretty easy, right? So if there's nothing to hold them together, that's generally telling us that that's a non-polar covalent. Does that make sense? Okay. And that also, Sam, later on, I think question number 4 asks you about flammable. Things that are volatile a lot of times tend to be flammable as well, like gasoline and stuff like that. Okay? So for the same reason, because things that are in a gas phase are much easier to catch fire than things that are liquids or solids. So that's why volatile things also tend to be flammable sometimes too. Okay? Anyway, go ahead.
Okay, so when the atoms, they separate, because they separate easily.
How about instead of the atoms separating easily, the
Electrons?
the molecules, because this is a group of atoms joined together, right? This is a compound. Okay? But in that within that compound, neither one of those atoms really wants electrons more than the other one.
Okay.
Does that make sense?
But within that, like, when you separate them, does that create, like, the evaporation?
Yes. Trying to get this to go here and this to go here, that is evaporation, or that is turning something into a gas. Because we said for something to be a gas, what has to be true about this group and this group?
Yes.
How close are they?
Very not close.
Very not close. Yes. They're far away, right? And they also move fast. If they're holding on to each other, that can't happen. Okay? All right. Other questions? Did you have a question about the lab, or was
I
that
have a
it?
question about number 3.
Okay.
No, you asked.
Okay.
If flammable.
The flammability one, yeah, it goes along with this a lot too. Okay. Paige, go ahead.
So would that be the same for the polar covalent?
Now,
Just
polar covalent. Let me do this for polar covalent. Oh. Lucky you get to watch this at home. I know all of you are gonna go home, rush home and watch this.
I will.
I'm gonna watch it.
Maybe at the end I'll have Lexi tell some more of her jokes, just to entertainment. So like when I read the description, I'll be like, stay tuned for the end. All right. pictures represents things held together by ionic bonds. One of these pictures represents things held together by polar covalent bonds. Okay? Lexi, which one?
Polar covalent on the right.
Polar covalent on the right, and then that means
Ionic.
ionic on the left. Okay? So these are held together by ionic bonds, and then these are polar covalents. So, Lexi, do you understand this by looking at the picture, or do you just remember on Friday we talked about this?
I understand it by looking at the picture.
Okay, so, do you want to explain it, or do you want me to explain it?
You can.
Okay, so, if something's polar covalent, what kind of bonds is it holding them together?
That's kind of honest.
It's in the name.
Ionic bonds.
If something is a polar covalent molecule,
Oh, I
that
thought
means
you said
it's a
ionic.
covalent bond.
I thought you
But it becomes polar because, now Addie, like we talked about here, these two have very similar electronegativities, but here, there is, in the polar covalent, there is a difference in electronegativity. What does that mean happen? What does that mean happens? One of them has a greater attraction than the other one. And that means, right, here in this blue egg, the side that's bigger is labeled negative, because what's happening towards that side of the molecule?
The electrons are staying closer.
Electrons
to
are
that.
sliding closer to that side, greater electron density. Now, the thing, and that makes it quote unquote negative, right? So really we should, we could, if we stay consistent with what we were talking about, we'd label it that way. Now, here, look, this is positive, this is labeled positive, and this is labeled negative. How is this picture different than this picture? John?
In the polar covalent, it's all one thing. Well, the ionic, they're separate particles.
In the polar covalent, right?
Whoa. Ho. That is crazy.
In the polar covalent, the positive and the negative part are both part of the same molecule, the same thing. Does that make sense? Right? They're both different parts of the same blue blob. But if I take it over here, right? There's a separate positive part right there and a separate negative part right there. That's characteristic of ionic bonding. Those are ions. Here, right, they're not a separate positive charge and a negative charge. They're just different parts of the same thing, and that's how I can distinguish between the picture on the left being ionic and the picture on the right being polar covalent. Okay, go ahead.
Why they like the double-headed arrows?
Yep.
In between? Is it like?
Go ahead.
Wait, no. What is that?
Okay, so now, you're talking about like this, and this, right?
Yeah. Do they like actually attach themselves? And
Yes, but not as strongly as like this attachment, right? Because that attachment right there, I should maybe do it a different color. This attachment right here, that's an attachment between something that is actually positive and something that is actually negative. That's a strong attraction. Here, that's an attraction between something that's kind of positive and something that's kind of negative. Which one's going to be a stronger attraction?
the more positive.
The ionic one, right? And that means which one is easier to separate? The polar covalent. Yes, they do attract each other a little bit, but not as strongly as like the ions in an ionic solid attract one another. So because these are easier to separate, that means they have lower melting points, lower boiling points, because it's not as hard to separate them. Does that make sense? Okay. Yes, they do hold on to each other because they're kind of positive and kind of negative, but not nearly as strong as the ions hold on to each other. Okay. Lexi, go ahead.
Would ionic be a solid and polar covalent be a liquid?
We can almost think of it that way if you want to. And then if nonpolar covalent would be what? Because it's a lot easier to separate, right? If it's just like this, this, and this, right? The polar covalent ones are egg-shaped because why?
They have different amounts of electrons.
Different amounts, let's go down, different amounts of electrons, different areas of electronegativity, which causes them to have different areas of electron density. Is that good? So it's higher, more electrons show up over on this side. Not that there's physically more electrons though. Yeah, I forgot I was on that one. But here, is there one side bigger than the other side? No, because not one side has more electrons than the other side. Does that make sense? Okay. So yeah, Lexi, if we wanted to think of it that way, things that are nonpolar covalent generally tend to be gases, or turn into gases pretty easily. Things that are polar covalent, you could think of them maybe as liquids, okay? But they can be turned into gases pretty easily. Guess what is a polar covalent molecule that you're pretty familiar with? Water, okay? But then things that are ionic tend to be solids at room temperature, especially because there's a really strong attraction there and it's hard to separate those ions out. Okay. What else? Eric, question, go.
So in those blobs, are
Yep.
so those are two atoms? in
Yeah,
one thing?
those are two atoms, and here, get rid of this craziness. Oh, yeah. In this blob, here, we'll spotlight it again. This is two atoms held together by a covalent bond. So that is a molecule. Oop. This is two atoms held together by a covalent bond with a big red stripe through the middle of them. That is a molecule. That's two atoms held together by a covalent bond. That's a molecule. So all of these are molecules. But over here, right, you can't really tell which one of the positives is attached to which one of the negatives because they're all sort of attached to each other. Does that make sense? Okay. So yes, that's two, yeah, to answer your question. Lexi, go ahead.
Ionic structures called crystal lattice.
Yep, that picture is a crystal lattice or a crystal.
What's the polar structure?
The only structure that exists in a covalent bond is the molecule itself. So that's like each of these individual blue blobs, okay? We talk when we're talking about covalent molecules, we talk about intermolecular forces because it's forces between those molecules. Does that make sense? Okay? Polar covalent molecules have intermolecular forces that holds them together. Nonpolar covalent molecules have very, 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 very small intermolecular forces, so they don't really hold on to each other very much at all. Does that make sense? Yeah. Paige, good.
Okay, on the,
New question, Paige?
no, it's about
Oh,
crystal.
Hi.
that would have been worth having a video. All right, Paige, go ahead. Finish this up.
It says, describe a crystal lattice and how does it relate to formula units?
Okay, so describe the crystal lattice. This is a crystal lattice. Okay, this three-dimensional arrangement of positives, negative, positive, negative, positive, negative, positive, negative. Ionic compounds, right? Or it's a arrangement of cation, anion, cation, anion, cation, anion. Okay? And like we talked about on Friday, it's real hard to tell that this specific positive is attached to this specific negative, because it's really not. Okay? But if we look at this, because this is a molecule, or sorry, this is a crystal of NaCl, within this crystal, there will be just as many sodiums as there are chlorines. Okay? This we call the formula unit. Okay? And that tells us the ratio of cations to anions shows up in the crystal. Does that make sense?
Mm.
So, it's just a ratio.
Yeah, because you can't necessarily say in this picture, or page, you can't necessarily say that this positive is attached to that negative. You can't say that, because that's really not true. But if you looked overall at the entire crystal, you would see that there is just as many sodium plus ones as there are Cl minus ones. This is the formula unit. It's the formula that you get when I say, okay, potassium, oxygen, what's the formula going to be? And you do the charges and you figure that all out. That's the same formula, that's the formula unit, but in real life, we can't say that like one sodium is attached to one chlorine. It's really not. But in this whole thing, there's just as many sodiums as there are chlorines. So when you're talking about a crystal, the formula unit tells you the ratio of cations to anions. Is that good?
Yeah.
Okay. Brian, go ahead.
Well, if you had two, like the sodium and the chlorine atom, and they were like bonded, it was just those two, would they be a molecule?
No, because a molecule is specifically held together by covalent bonds. But, right, like I guess the idea would kind of be the same, but in nature that really doesn't happen. You don't just get one sodium and one chlorine that are attached to one another and not to anything else. Okay? But then like here in something like this, although Ryan, that's like you have like the idea of what a molecule is based on that question. Just keep in mind that a molecule is only going to contain nonmetals as opposed to metals. Okay? Something like this, MgCl2, magnesium chloride, would have one magnesium for every two chlorines in this crystal, because that's how many they need to balance out the positives and negatives. So Paige, this is the formula unit for magnesium chloride. It would give you the ratio of positive cations to negative anions.
So would we have to do any tests to figure?
Not like from a picture, but like we did a lot of earlier in this unit say, okay, what if I give you, lithium, and then I give you sulfur, what would be the formula in the name of that compound, right? And you find lithium on the periodic table and find out how many valence electrons it has. You find sulfur on the periodic table and find out how many electrons it has, which one's positive, which one's negative, blah, 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 right? You're basically figuring out what the formula unit is going to be for that compound. Okay? And just to, that's what it ends up being. Yep. All right, Lexi, same question or different question?
I kind of.
Okay, go ahead.
It says explain the difference between a molecule and a formula.
Okay, so Brian, do you want to handle this question or?
No.
Okay. So the difference between here. Actually,
Like the fourth one.
Fourth or fifth and the third one.
okay. Molecule and formula unit. First, if we're identifying whether I give you a formula and whether it is a molecule or a formula unit, you can kind of tell just by looking at the formula. Okay? What kind of elements will molecules have in them? Well, if they're okay, molecules will have nonmetals plus nonmetals in them, but a formula unit would have what? A metal and a nonmetal. Is that good just for like identifying them to begin with? Okay. And then, so Lexi, going back to this picture, okay? each one of these blue blobs is a molecule, because it's one group of atoms, non-metals, held together by a covalent bond. They are completely separate from every other group that is held together by a covalent bond. Okay? They might attract each other, but they are independent of one another. Okay? But a formula unit is embedded within this crystal, and it's just a small piece of this bigger crystal. Does that make sense? Okay? So a molecule deals with a group of atoms that are covalently bonded. A formula unit deals with a group of atoms that are ionically bonded. Does that make sense? And a formula unit is more kind of like a ratio within that big crystal. So like Ryan said, like if you could isolate one sodium and one chlorine, that would kind of be like an ionic molecule, just one sodium and one chlorine, but that doesn't happen in nature. Like it's never just one sodium and one chlorine. But for covalent things, that happens all the time. They are an independent group. They might interact with one another. Water interacts with other water molecules, but that grouping is H2O each time. Does that make sense? Okay. All right, so what else? Page good.
Predict an element's reactivity by examining the number of atoms or atoms.
Predict an element's reactivity by examining the number of valence electrons. From a valence electron standpoint, what is every element looking for?
The lowest energy level.
Ultimately, we're looking for 8 valence electrons.
It's for the lowest.
Because, Ryan, that means that
They will have the lowest possible energy
that is a low energy state.
state.
Okay? That is a low energy condition. So, Paige, things that, looking at a number of an element's valence electrons can tell you how reactive, because reactivity is the process of those elements either gaining or losing electrons, gaining, losing, or sharing electrons in order to get to 8. Okay? So, like halogens, right? Okay, group 17. How many valence electrons do halogens have?
7.
They have 7. What are they looking to do?
Gain 1.
Gain 1. Halogens are very reactive because they only need to gain 1 electron. They're very close to having 8. That doesn't make them more stable, that actually makes them less stable because they want that one last electron. Alkali metals, way on the other side, right? They only have 1 valence electron, but what are they looking to do with that valence electron? Lose it. So alkali metals are also very reactive because they're very close to having 8. If they dump that 1 electron, now they've got 8. Okay? So reactivity comes into, reactivity is an object losing, gaining, or sharing electrons to get to 8. Things that are real close to 8 are very reactive. Things that are farther away, not so much.
What would be on the test that we have to know about? Or just
No, that's a perfectly fair question, Mitch. So, okay. Which of those 4 elements is the most reactive?
So, calcium.
Discuss with yourselves. Go.
Sodium, because it only needs to get rid of 1, it really wants to get rid of that 1.
And it's not neon, because that's got a full electron shell.
It's not. Get it?
Right, answer, you have another question. Okay. All right, so let's discuss. Okay. So first, Sean, I heard you talking. We can eliminate one of these right away. Which one?
Neon.
Okay. It's not neon, right? Neon is not reactive at all. It already has 8 valence electrons, right? Okay. So, Eddie, where are we going with the other 3?
What do you mean?
Which one's going to be the most reactive?
Sodium,
Okay, sodium is going to be the most reactive. Why?
because it's in the first column group family, so it's going to have the most reactivity.
How close is it to having 8 valence electrons?
It just needs to lose.
It just needs to lose 1, and then it's got 8. That makes it really reactive. Okay. So, Paige, that would be like a question that I could ask you by determining an element's reactivity based on its number of valence electrons. Okay. Let's go.
So would like 3, 4, 5, 6, and like 8 valence electrons be low energy?
Now, 8 valence electrons is super low reactivity, right? We said that those elements don't react with anything at all, right? But things in this section, like right here, right? They're not real reactive because you got to either lose 3 or gain 5, or it's hard to do that, especially because for every electron that you lose or gain, all the other stuff in the atom reacts to that, right? For nitrogen has 5 valence electrons. It's got to gain 3 more to get to 8. So if it gains 1, now it's got 6 valence electrons. It's closer to being stable, but all the electrons that nitrogen already has, like the 7 that are already there, they don't like that 8th electron. Because what are they trying to do? What do all electrons do to each other? They repel. So nitrogen may be closer to being stable by having 8 electrons, but all the electrons that were already there don't like that extra electron. So is it real probable then that nitrogen's going to pick up another electron? No, because let's see, the ones that it already had didn't like the extra one it picked up to begin with. Is it going to like it if they picked up a second extra one?
It's actually trying to get 5 more. Or 3 more.
Wow.
What was it?
I don't know. It wasn't like a warning signal or anything like that. If not, we'll be recorded for posterior sake. So, for posterity. So that's history of Whittle. So. Our last conversation dealt with
Okay.
bonding. So
I want to die.
Last words are said.
yeah. So Lexi, not just you, but that's why those ones won't be that reactive, because they got to figure out how they're going to get to 8 electrons without upsetting all the electrons that are already there already. Okay? But
Why are most chemical reactions exothermic?
all right. So explain why most chemical reactions are exothermic. What do we say that? What is the reason why elements form bonds? What are they looking to do?
The lowest
Get lower energy. They do that by getting 8 valence electrons. Hey. Hey. I'm trying to record it, guys. You're getting up. He's laughing.
I'm much
So, we said that elements bond with one another because they're trying to get to a lower energy state. But energy is a conserved quantity, right? Conservation of energy. So if it has high energy and then it bonds with something and now it has low energy, that energy can't just go away, right? It's got to go somewhere. What did we say that exothermic meant? Do you remember?
Heat produced.
It's releasing heat, or heat is going out of it. So the energy that it goes down because it becomes more stable is released, and that's why it's exothermic most of the time. Because as they're bonding together, they're becoming more stable, they're giving off energy because now they're in a lower energy state. Is that good? All right, one more? We have time for one more. Paige, go ahead.
It's not really on the objective sheet.
Okay.
But do we need to know the octet rule and duet rule?
Octet rule and duet rule is just a fancy way of saying how many electrons do I have to gain or lose to get to 8. Okay, octet 8, right? That's just the idea that elements are going to either gain or lose electrons or share electrons to get to 8. Okay. All right, good there?
good there.
So tomorrow morning, I have meeting during first period tomorrow morning, but I will be in this room before school. So if you got questions, go ahead and email, or go ahead and come and see me tomorrow morning. You could email me tonight. I do have a couple things to do tonight, but I'll probably get back to you before I go to bed. So it probably won't be real early. So. All right, study hard, everybody. I'll see you guys tomorrow.